Soft starters are static starters that accelerate, decelerate, and protect three-phase induction motors. The control of the voltage applied to the motor by means of adjustments to the firing angle of thyristors allows the soft starter to start-stop an electric motor smoothly. With adequate adjustments of variables, the torque produced is adjusted to the needs of the load, so that the required current is going to be the lowest possible for the starting procedure. A soft starter does not change the frequency or the speed like a drive. Instead, it ramps up the voltage applied to the motor from the initial voltage to the full voltage. Initially, the voltage to the motor is so low that it's only able to adjust the play between the gear, wheels, or stretching driving belts. To avoid sudden jerks during the start, gradually, the voltage and torque increases so that the machinery starts to accelerate. One of the benefits with this starting method is the possibility to adjust the torque to the exact needs. Whether the application is loaded or not, using a soft starter will reduce the starting current and thereby avoid voltage drops in the network. It will also reduce the starting torque and mechanical stress on the equipment, resulting in reduced need for service and maintenance. Just as for a drive, the soft starter can perform a soft stop, eliminating water hammering and pressure surges in pumping systems and avoiding damage to fragile material on conveyor belts. A soft starter consists of only a few main components. There are the thyristors that can regulate the voltage to the motor and the printed circuit board assembly, or PCBA, that is used to control the thyristors. In addition to this, there are the heat sink and the fans to dissipate the heat, current transformers to measure the current, and sometimes display and keypad, and then the housing itself. It is more and more common to offer integrated bypass contacts in the main circuit, minimizing the power loss in normal operation. Depending on the model of the soft starter, it can be equipped with a built-in electronic overload relay, eliminating the need for an external relay, PTC input, fuel bus communications, possibilities also, and more. Soft starter functionality. A soft starter consists of a number of anti-parallel thyristors, 2 in each phase. These thyristors are semiconductor components which normally are isolating, but by sending a firing signal, they can start to conduct, allowing the voltage and current to pass through. When performing a soft start, the firing signal is sent to the thyristors so that only the last part of each half period of the voltage sinus curve passes through. Then, during the start, the firing signal is sent earlier and earlier, allowing a bigger and bigger part of the voltage to pass through the thyristors. Eventually, the firing signal is sent exactly after passing 0, allowing 100% of the voltage to pass through. By allowing more and more of the voltage to pass through the thyristors, this can be seen as ramping up the voltage from something called the initial voltage to the full voltage. When performing a soft stop, the opposite happens. At first, the full voltage is allowed to pass through the thyristors As the stop proceeds, the firing signals are sent later and later, allowing less and less of the voltage to pass through until the end of the voltage is reached. Then, normal voltage is applied to the motor, and the motor stops. Since the voltage to the motor is reduced during start, both the current and the torque will also be decreased. In fact, if the voltage is decreased by 50% of the full voltage, the current will be decreased by 50% of maximum current. At that speed, and the torque would be decreased to about 20% of maximum torque. Benefits of using a soft starter. The inrush current is reduced so that voltage drops on the network are avoided. The torque is reduced, which will decrease the mechanical stresses on the equipment and lead to a reduced need for service and maintenance, and also to a longer life of the equipment. Finally, by using a stop ramp, water hammering is avoided in pump systems, which will further reduce the stress of the equipment. Torque control. Normally, a soft starter performs a start and a stop by ramping up and down the voltage linearly. However, a linear change of voltage does not necessarily give a linear change of torque or of the speed. This is where torque control comes in, with a torque ramp. It is not the voltage that is ramped up or down linearly. It is the torque. This is done by using a regulation loop where the torque is calculated by measuring both the voltage and current. This torque is then compared to the required torque, and the voltage is adjusted so that the torque is changed in the required manner. Torque control is especially useful for stopping pumps where a sudden decrease of the speed may lead to water hammering and pressure surges that can cause tremendous mechanical wear on the pump, the valves, and the pipe system. When performing a stop with a normal voltage ramp, the voltage starts to decrease as soon as the stop command is given. However, as the voltage decreases, the current will instead increase. This is because the motor will try to remain in its current state. Since torque depends on both the voltage and the current, it will remain more or less unchanged. Then, after some time, when the voltage has dropped enough, there will be a sudden drop in current and the torque, and the motor will stop suddenly. This stop will still be far better than a direct stop, but in many pump systems this is not good enough. So another solution must be found. With torque control, it is not the voltage that is ramped down. It is the torque. This will force the motor to slow down immediately and perform a controlled deceleration all the way until it comes down to a complete stop. Being able to have a good control of the torque of the motor is crucial to being able to prevent water hammering. However, this is not enough. What is also needed is a torque curve that has been designed in such a way that the water hammering is avoided. In fact, a linear decrease of the torque is not a very good way to stop a pump. This is why some manufacturers for a long time have worked closely together with pump manufacturers in order to gain knowledge about how to best stop pumps. After more than 1,000 different tests and simulations with different combinations of pumps and motors, some manufacturers have developed the optimal stopping curve perfect way to stop the pump. All motors are used for starting and running different applications. Soft starters and conveyor belts. Conveyor belts can have a lot of different characteristics. Length can vary from only a few meters up to several kilometers, and the belt can be horizontal or inclining. Typically, the conveyor belt has a constant low torque with low to high braking torque, depending on the load. Direct online starting method. Conveyor belts often need starting torque very near or just above the rated torque of the motor. A direct online start with a normal squirrel cage motor gives approximately 1.5 to 2.5 times rated torque of the motor depending on motor size. When making a direct online start, there is a very high risk of slipping between the belt and the driving roll, depending on this high starting torque. Gearboxes and couplings are also exposed to high mechanical stresses. This results in considerable wear and tear, often high maintenance cost. Sometimes fluid couplings are used to reduce transfer torque. This method is expensive and requires a lot of maintenance. Since the start delta starter will reduce the torque in the start connection, it is not possible to use this starting method when the load torque is close to the rated motor torque during start. A start delta starter can only be used successfully with a very lightly loaded conveyor belt. By using a soft starter, the starting torque can be reduced to a minimal value and still be able to start up the conveyor belt. The setting feature of the soft starter makes it possible to adjust the torque to exactly the level that is necessary for the start. The result is the least possible stress on gearboxes and couplings and no slip belts during the start. This will reduce the maintenance cost to a minimum. When using a soft starter, you will receive approximately 3 to 4 times rated motor current during the start. In addition, some soft starters are equipped with phase reversal protection to protect conveyor belts running in the wrong direction. Soft starters may also have under or overload protection to detect if the load is too low or too high, and then kickstart to be able to start jam belts. Selection of a suitable soft starter. A conveyor belt can be both a normal start and a heavy-duty start depending on the characteristics. For a normal start, select the soft starter according to the motor in kilowatt ratings. For a heavy-duty start, select one size bigger. If more than 10 starts per hour are done, select one size bigger soft starter. Starting capacity and overload protection of a soft starter. Starting capacity of the soft starters. When starting a squirrel cage motor, there will always be a starting current, which is higher than the rated motor current. When first started, this starting current is typically 7 to 8 times the nominal current when starting a motor with a DOL or direct online starting method. This starting current is typically 7 to 8 times the nominal current, and when using a soft starter, it is reduced to 3 to 5 times the nominal current. Depending on the application, the start can be short or long. Since the current is higher during the start, the soft starter will warm up during the start. It is very important to select a soft starter with thyristors and heat sinks dimensioned for the motor and the start performed. Soft starters should be upsized one size when used for heavy-duty applications, since the start then usually is longer. The maximum permitted starting current for a soft starter depends on the starting time. The voltage or current to the motor is not affected by selecting a bigger soft starter. The only difference when selecting a bigger soft starter is that the soft starter is dimensioned to cope with a higher current for a longer time, and thus being able to start bigger motors or heavier applications. The overload protection for the motor, thermal or electronic, will very often set the limit of the starting capacity. These overload protections have different tripping classes, describing how fast they are tripping for a specific current. A Class A relay is used for normal start in general, while a Class 30 is used for heavy-duty starts, where the start usually is longer. In some applications where the overload protection is bypassed, all the protection is active. During start, to achieve a longer reliable start time, it is particularly important to check the soft starter starting capacity, since this will be the limitation. Location of main contactor. When using the soft starter inside Delta, there are two options for the main contactor: inside the Delta circuit or outside. Both locations will stop the motor, but in alternative A, the motor is still considered to be under tension. In alternative B, the main contactor must be chosen according to the rated current of the motor, while the contactor in alternative A can be chosen according to 58% of the rated current. Regardless of where the main contactor is placed, it should be AC-3 rated for that current to be able to break the current and stop the motor in an emergency. Starting several motors. In some applications, it is desired to start several motors with one soft starter in parallel with each other or in sequence. This is often possible to do, but some data has to be taken into consideration. Parallel start. If a soft starter is going to be used for starting several motors at the same time in parallel mode, there are two important parameters to check. First, the soft starter must be able to cope with the rated current for all motors together. Second, the soft starter must be able to cope with the starting current for all motors together until rated speed is achieved. Sequential start of motors. If the soft starter is going to be used for starting several motors one by one, sequential start, it is important to check that the soft starter is able to cope with the starting current for each motor during the whole starting sequence. Some soft starters, like the PSD-B range, have the possibility to use different parameters set for the different motors. This is needed to achieve a good start if the motor sizes are different or if the applications are different. Most soft starters cannot soft stop more than the latest started motor. Usually, separate protections need to be used for each of the motors. Connection of control circuits to the soft starter. Control supply. The control supply voltage is the voltage supplied to the circuit board, fans, etc. in the self-starter. The terminals are usually marked 1 and 2. A common voltages is 100 through 250 AC volts. Control circuit. The control circuit is used to give a start and stop signal to the self-starter and sometimes to give other input signals. Depending on the self-starter, the control voltage may be taken from the self-starter itself or may be supplied externally. Most often, the control voltage is 24 volts DC. Also, depending on the self-starter model, the signals required may need to be maintained or it may be enough with a pulse. Output signal relays. There are sometimes up to 3 different output signals that can be received from the self-starter. Analog output. Some self-starters are equipped with an analog output signal that can be connected to an analog meter or be used as an analog input to a PLC. This analog output can be used to see the current to the motor on an analog current meter, eliminating the need for an external current transformer. Connecting a self-starter to a fuel bus system. Today, many self-starters can be connected to a PLC using a fuel bus system such as Profibus or Modbus. Depending on the self-starter and the fuel bus protocol, it may be possible to start and stop the self-starter. To see status information and to change the setting of the self-starter from the PLC to connect to the self-starter to a fuel bus system, the fuel bus plug is used. Two-phase control versus three-phase control. Traditionally, a self-starter have used 6 thyristors, 2 anti-parallel connected in each of the 3 phases, to control the output voltage to the motor. However, in order to reduce the number of components used or to minimize the size of the self-starter, a solution where only 2 of the 3 phases are controlled is possible. In this solution, the third phase is just passing through the self-starter without controlling the voltage or the current. A self-starter controlling only 2 of the 3 phases is called a two-phase control self-starter, and it will function in the same way as a 3-phase control self-starter with a few exceptions. First, not possible to connect inside delta. Since one of the phases is not controlled by the self-starter, the current will pass through that phase without giving a start signal to the starter. This will not start the motor, but it would heat up the motor and eventually damage the motor. Even if a line contactor was to be used to avoid this during startup, the current will basically not be reduced at all when starting, and reducing the current perhaps is the most important benefit of using a self-starter. 2. Some two-phase control self-starters create DC components. When ramping up and down by controlling only 2 phases, a DC component will be created which will have braking effect during the torque and creating a very noisy bad start. Only very few two-phase control self-starters on the market are equipped with some sophisticated algorithm to eliminate this DC component. Slightly unbalanced currents during start. When using a three-phase control self-starter, the starting current will be balanced between the three phases. When using a two-phase control self-starter, however, the current will be higher in the phase that is not controlled and lower in the other two phases. This has the effect that the maximum current in one phase is higher with a two-phase control self-starter, or compared with a three-phase control self-starter. This imbalance will only appear during the short time of the start and the stop. And during continuous run, the currents will be balanced. The settings can be done either by adjusting potentiometers, changing dip switches, using a keypad, or a computer. Start ramp is the time from where the self-starter starts its ramp, or initial voltage, until full voltage is reached. The ramp time should not be too long, as this will only result in unnecessary heating for the motor and a risk of the overload relay tripping. A common misunderstanding is that this parameter sets start time, that is, the time for motor to reach full speed. This is not true. The start ramp parameter only sets the time until the self-starter applies full voltage to the motor. If the motor is unloaded, the start time for the motor will probably become shorter than the set ramp time. And if the motor is heavily loaded, start time will probably become longer. If the ramp time is set to 0, the stop will be like a direct stop. Torque control is a function that will control the torque of the motor instead of the voltage. This is especially useful when stopping pumps in order to avoid water hammering. On self-starters with torque control, it is possible to select between a torque ramp or a voltage ramp, both during start and stop. These parameters are called start mode and stop mode. Initial voltage. Initial voltage is sometimes named pedestal voltage. This is the point from where the self-starter starts to ramp up. The torque of the motor will drop with the square of the voltage. And if the voltage is set to null, for example 20%, the starting torque will become 0.2 equals 0.0 or 5 or 4% only. And the motor will now start from the very beginning. Therefore, it is very important to find a level that is just high enough to make the motor take off directly to avoid unnecessary heating. End voltage is the voltage level that the self-starter ramps down to during the set ramp time of a stop ramp. At this point, the motor shall already have stopped, and the self-starter will break the current to the motor in order to avoid unnecessary motor heating. Adjustable rated motor currents. This makes it possible to set the motor rated current on the soft starter for the used motor. This setting will affect other values as well, such as the trip level of the electronic overload protection and other protections, but also the level of the current limit function. Current limiting. Current limiting can be used in applications where a limited starting current is required, or at a heavy-duty start when it is difficult to achieve a perfect start with the setting of the initial voltage and the start ramp only. When the current limit is reached, the self-starter will temporarily stop increasing the voltage until the current drops below the set limit, and then continues ramping up the voltage. Since the maximum current, DOL current, is decreasing as the speed increases, the voltage can be gradually increased without exceeding the set current limit. Something to consider when installing soft starters are harmonics. Harmonics are unwanted voltages and currents existing in almost every electrical system today, and are always a multiple of the rated frequency. Typical harmonics are third, fifth, seventh, ninth, etc. The harmonics contribute to the unnecessary heating of motors, cables, and other equipment, and may shorten the life of these devices if exposed for a long period of time. It can sometimes also disturb functions in electronics and systems. The harmonics content and the level naturally depend on the source, but also on several other parameters such as the impedance in the feeding network, motor, capacitors, and other devices such as the system altogether. In other words, a quite complex phenomenon. As always, thank you guys for watching. Please like, share, subscribe. See you in the next one.